Hey everyone, today's journey ventures into the airless void, and extremes of Mercury. We begin with why you'd never want to walk on the surface of Mercury, as we unravel the planet's harsh truths. Before you get comfortable, please like this video, and subscribe for more cosmic voyages. Now dim the lights, wrap yourself in something cozy, and let the crackling fire guide your mind toward calm. Prepare to drift into rest, as we navigate Mercury's unforgiving surface. We'll discover how the lack of atmosphere, blistering daytime heat, and frigid nights make any step fatal. Mercury sits as the innermost planet in our solar system, silently orbiting closest to the Sun. Its proximity to our star makes it one of the most hostile environments in our planetary neighborhood. Astronomers have studied this small rocky world for centuries, gradually unveiling its extreme characteristics. Mercury exhibits conditions that would make any human exploration exceptionally dangerous, even with our most advanced technology. The planet completes an orbit around the Sun in just 88 Earth days, making it the fastest moving planet in our solar system. This rapid journey through space exposes Mercury to intense solar forces, shaping its inhospitable landscape. Scientists measure Mercury at just 3,700 miles in diameter, making it slightly larger than our Moon. This small size contributes to its inability to hold onto a substantial atmosphere, leaving the surface exposed to space. One of the first major challenges for any visitor to Mercury would be the complete absence of air. Mercury possesses virtually no atmosphere, just an extremely thin exosphere containing traces of oxygen, sodium, hydrogen, helium, and potassium. This exosphere is so tenuous that it cannot be considered a true atmosphere, as its particles rarely collide with one another. The lack of a substantial atmospheric layer means there is nothing to protect the surface from the harsh conditions of space. Without an atmosphere, Mercury experiences several immediately life-threatening conditions. The absence of air means no protection from cosmic radiation, no regulation of temperature, no sound transmission, and no breathable oxygen. Any human explorer would require a completely self-contained life support system, far more robust than those used on lunar missions. The engineering challenges of creating a spacesuit capable of withstanding Mercury's environment would be enormous. The history of Mercury observation dates back to ancient times, with the earliest known records coming from the Assyrians around the 14th century BCE. The planet received its name from Roman mythology, where Mercury served as the swift messenger of the gods. This name aptly describes its rapid orbital period around the Sun. Modern scientific understanding of Mercury dramatically improved with the Mariner 10 mission in 1974, which provided the first close-up images of the planet. Later, the Messenger mission, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging, orbited Mercury from 2011 to 2015. This mission revealed crucial details about the planet's composition and environment. Currently, the European and Japanese Bepi Colombo mission is en route to Mercury, expected to provide even more detailed information when it arrives in the mid-2020s. Each mission must overcome significant technical challenges due to Mercury's proximity to the Sun. The solar radiation near Mercury presents the first major obstacle. Mercury receives approximately 7 times more solar energy per square meter than Earth does. This intense bombardment of energy creates surface conditions that would quickly overwhelm conventional space equipment. Solar radiation, which means high-energy light and particles from the Sun, pounds down on the surface without any atmospheric filter to weaken it. This radiation would damage both electronic equipment and human tissue within minutes of exposure. Scientists measure the solar constant, which is the amount of solar energy received per unit area, at approximately 9,300 watts per square meter on Mercury. For comparison, Earth receives about 1,360 watts per square meter. This 7-fold increase creates an environment where unprotected materials would quickly degrade or melt. Even reflective surfaces would struggle to manage this heat load over extended periods. The complete absence of atmospheric pressure on Mercury creates additional hazards. Human physiology requires ambient pressure to function properly. In a vacuum or near-vacuum environment like Mercury's surface, the human body would experience immediate and catastrophic effects. Blood would boil at body temperature, tissues would swell, and consciousness would be lost within seconds. This phenomenon, known as ebullism, means that any breach in a spacesuit would be rapidly fatal. Mercury's surface bears the marks of countless meteor impacts, preserved perfectly due to the lack of erosion from wind or water. These craters create a rugged, uneven terrain that would make traversing the surface extremely challenging. Without atmospheric drag to slow them down, even tiny micrometeorites, which are small particles of space dust, strike the surface at full cosmic velocities. This bombardment continues to this day, creating an additional hazard for any surface explorers or equipment. The planet's weak magnetic field offers minimal protection from charged particles streaming from the Sun. Mercury's magnetic field measures at just 1% the strength of Earth's, too weak to deflect the solar wind effectively. This magnetic field has a strange offset, centered about 480 kilometers north of the planet's center, creating an asymmetrical protection pattern that leaves some areas more exposed than others. Scientists still study this unusual magnetic configuration to understand its formation. The communications delay between Earth and Mercury varies significantly, depending on the relative positions of the planets. At their closest approach, the delay measures around 5 minutes each way. At their furthest, this delay stretches to around 14 minutes. This communication lag would make real-time assistance impossible during emergencies. Any human or robotic mission would need substantial autonomy to operate safely on the Mercurian surface. Mercury follows a highly elliptical orbit around the Sun, more stretched than most planets in our solar system. This orbital path takes Mercury as close as 29 million miles from the Sun at perihelion, its closest approach, and as far as 43 million miles at aphelion, its furthest point. This variable distance creates fluctuating conditions that would complicate any mission planning. The solar intensity changes by about 60% between these orbital positions. Passage 2. The absence of a substantial atmosphere on Mercury drives many of its most extreme conditions. Atmospheres serve multiple protective functions for planets, regulating temperature, blocking radiation, and preventing small meteorites from reaching the surface. Mercury lacks all these protections due to its small size and proximity to the Sun. The planet's low gravity cannot hold onto gas molecules, allowing them to escape into space over time. This atmospheric scarcity means the surface experiences raw exposure to space. Any mission to Mercury would need to account for this complete lack of environmental buffering. The airless vacuum prevents heat distribution across the surface, contributing to the extreme temperature differences between sunlit and shadowed areas. Thermal management would become the primary engineering challenge for any Mercury exploration equipment. Without an atmosphere to scatter light, the sky on Mercury would appear black even during daytime, with stars visible alongside the blindingly bright Sun. This visual environment would create challenging conditions for human operators or camera systems. The extreme contrast between light and shadow would make navigating the terrain difficult, with deep shadows potentially hiding hazardous features. This lighting situation complicates both remote operation and autonomous navigation systems. The lack of atmosphere also means no weather systems exist on Mercury. There are no winds, no clouds, no rain, and no erosion from these forces. This absence of atmospheric processes means that surface features remain relatively unchanged for millions of years, preserved in the vacuum of space. Impact craters from billions of years ago appear almost as fresh as those formed more recently, creating a time capsule of solar system history. Sound cannot travel through Mercury's vacuum. Any explorer on the surface would experience complete silence, except for vibrations conducted through their spacesuit or through direct contact with the ground. This auditory isolation adds another layer of sensory deprivation to the already alien environment. Communication would rely entirely on radio transmission, with no backup option of vocal communication even between nearby explorers. The planet's exosphere, while technically present, provides none of the benefits of a true atmosphere. This extremely thin layer of particles extends thousands of kilometers above the surface, but remains too sparse to interact with the surface in meaningful ways. The exosphere contains elements that have been blasted off the surface by solar radiation and micrometeorite impacts. Scientists study this tenuous layer to understand more about Mercury's composition and the processes affecting its surface. Surface pressure on Mercury measures less than 1 femtobar, or 1/4,000,000th of Earth's atmospheric pressure at sea level. This near-perfect vacuum creates conditions where materials behave differently than they would on Earth. Lubricants would evaporate, metals would cold weld together, and electrical systems would face unique challenges. Engineering for this environment requires specialized materials and designs not needed for missions to planets with atmospheres. The absence of an ozone layer or any atmospheric filtering means that the full spectrum of solar radiation reaches Mercury's surface. This includes dangerous ultraviolet radiation, X-rays, and other high-energy electromagnetic waves that would damage living tissue. Earth's atmosphere blocks most of these harmful wavelengths, but on Mercury, they strike the surface unimpeded. This radiation would quickly damage unprotected organic material and many synthetic materials as well. Mercury's tenuous exosphere undergoes constant change. Solar radiation pressure pushes atoms away from the day side, creating a comet-like tail extending away from the sun. This dynamic process continually strips material from the planet, though at such a slow rate that Mercury has maintained its current state for billions of years. The interaction between the solar wind and Mercury's surface contributes to the composition of this minimal atmosphere. The surface of Mercury bears a superficial resemblance to our Moon, heavily cratered and grey in appearance. However, closer examination reveals significant differences in composition and structure. Mercury has a much higher density than the Moon, indicating a large metallic core comprising approximately 70% of its mass. This large core generates the planet's weak magnetic field and influences its surface properties. Without atmospheric protection, the surface of Mercury experiences direct exposure to the solar wind. The solar wind consists of charged particles streaming outward from the sun at speeds of 300 to 800 kilometers per second. These particles interact with surface materials, causing changes in their chemical composition over time. This process, called space weathering, gradually darkens and reddens surface materials. The lack of atmosphere means no protection from cosmic radiation either. Cosmic rays, which are high-energy particles from outside our solar system, constantly bombard Mercury's surface. These particles can penetrate meters into the regolith, the layer of loose material covering the bedrock. Over billions of years, this radiation has altered the chemical composition of surface materials. Any human explorer would need substantial shielding to avoid dangerous radiation exposure. Mercury's regolith, the layer of pulverized rock covering the surface, has been created entirely by meteor impacts and radiation damage. Without water or wind erosion, mechanical breakdown from impacts remains the primary weathering process. This regolith behaves differently than soil on Earth, with sharp, jagged particles that would quickly abrade spacesuit materials and mechanical components. The fine dust would pose significant challenges for any moving parts in exploration equipment. The complete lack of organic material on Mercury's surface creates an environment devoid of any biological contamination. This sterile landscape presents an opportunity for scientists studying the pure geology of a rocky planet, but also means no indigenous resources for potential human use. Every necessity for human survival would need to be transported from Earth, making any crewed mission extraordinarily complex and expensive. Without an atmosphere to hold and distribute heat, temperature extremes on Mercury become the next major challenge for exploration. The surface temperature variation stands as the most extreme in the solar system, ranging from scorching heat in the sunlight to cryogenic cold in the shadows. This temperature gradient can exist over just a few meters of distance, creating extraordinary thermal stress on materials and equipment. Passage temperature extremes represent the second major obstacle to Mercury exploration. The daylight side of Mercury experiences temperatures hot enough to melt lead, reaching up to 430 degrees Celsius, or 800 degrees Fahrenheit. This extreme heat results from Mercury's close proximity to the sun and the lack of atmospheric insulation. The intensity of solar radiation creates surface conditions that would rapidly destroy conventional equipment and certainly prove fatal to any unprotected human. The temperature variations on Mercury exceed those found anywhere else in our solar system. The thermal range spans approximately 600 degrees Celsius, or 1,100 degrees Fahrenheit. This massive swing occurs because the airless environment cannot distribute heat across the planet. Each spot on the surface heats or cools independently based solely on its exposure to sunlight. This creates a patchwork of temperature zones that would complicate any exploration efforts. Mercury rotates extremely slowly compared to Earth. A single Mercurian day, from sunrise to sunrise, lasts approximately 176 Earth days. This prolonged exposure to sunlight allows the dayside surface to absorb enormous amounts of heat. The lack of atmospheric convection means this heat has nowhere to go except to radiate back into space, creating the scorching surface temperatures. The slow rotation ensures that the heating process continues for what would be months on Earth. The thermal conductivity of Mercury's surface material means heat penetrates only a short distance below the surface. Just a meter beneath the sun-baked ground, temperatures remain relatively constant and cool. This temperature gradient creates a challenging engineering environment where materials must withstand both extreme heating on exposed surfaces and much cooler conditions underneath. The stress from this thermal differential can cause materials to crack or deform over repeated heating cycles. Surface materials on Mercury respond differently to these temperature extremes based on their composition. Dark materials absorb more solar radiation and heat more quickly than lighter materials. This differential heating contributes to the breakdown of rocks over time through thermal stress. Scientists studying Mercury's surface need to account for these thermal processes when interpreting data about surface features and composition. The constant heating and cooling cycles create unique weathering patterns not seen on Earth. The extreme heat on Mercury's day side would cause most metals to weaken significantly. Aluminum, commonly used in spacecraft construction, loses approximately half its strength at just 200 degrees Celsius, well below Mercury's dayside temperatures. Even titanium, known for its heat resistance, begins to lose structural integrity at temperatures found on Mercury's sunlit surface. These material limitations severely constrain the design options for Mercury landers or rovers. Standard electronic components would fail almost immediately in Mercury's daytime heat. Silicon-based semiconductors, the foundation of modern electronics, typically have maximum operating temperatures around 125 degrees Celsius. Mercury's dayside temperatures exceed this limit by hundreds of degrees. Specialized high-temperature electronics would be required, using materials like silicon carbide or gallium nitride that can function at higher temperatures. These components remain limited in capability compared to conventional electronics. Battery systems face particular challenges in Mercury's thermal environment. Most battery chemistries cannot function at either the high or low temperature extremes found on Mercury. Lithium-ion batteries, commonly used in space applications, typically operate between -20 and 60 degrees Celsius. Mercury's temperature range extends far beyond these limits in both directions. Any Mercury mission would require either extraordinary thermal management systems or entirely new power storage technologies. Solar panels, the standard power source for planetary missions, face a dual challenge on Mercury. The excessive solar energy would generate more electricity than systems could handle, requiring robust power management. Simultaneously, the extreme heat reduces photovoltaic efficiency and accelerates degradation of the panels. These conflicting factors make power generation on Mercury paradoxically difficult. Despite the abundant solar energy, engineers must balance power production against thermal management needs. Mercury's surface heats unevenly due to variations in albedo, which refers to how reflective a surface is. Darker regions absorb more sunlight and heat more quickly than lighter regions. This creates temperature variations across the surface even during full daylight exposure. The uneven heating contributes to thermal stress in the surface materials, potentially creating new cracks and fissures over time. These thermal properties help scientists understand the composition of different surface regions. The heat from Mercury's surface radiates primarily as infrared energy. This radiation would quickly warm any nearby objects through direct thermal transfer. Even reflective materials would eventually heat up in this environment, as the infrared wavelengths penetrate many reflective coatings designed for visible light. This means that even equipment designed to reflect sunlight would still absorb heat from the surroundings. Thermal isolation becomes extremely difficult in such conditions. Mercury's slow rotation combined with its rapid orbital period creates a unique solar day. A single day-night cycle on Mercury lasts approximately 176 Earth days, while it orbits the Sun every 88 Earth days. This means that Mercury completes 2 orbits around the Sun for every 3 rotations on its axis, a relationship called a 3-to-2 spin-orbit resonance. This unusual rotation pattern creates complex heating and cooling cycles across the surface. The slow rotation of Mercury means that any given spot on the surface experiences extremely long periods of heating. A location on Mercury's equator would endure approximately 88 Earth days of continuous sunlight. During this extended period, temperatures would steadily climb until reaching equilibrium where heat absorption balances heat radiation. This prolonged heating cycle bakes the surface thoroughly, driving away any volatile compounds that might otherwise exist on the planet. The heat conductivity of Mercury's regolith plays an important role in temperature regulation. The surface layer conducts heat poorly, insulating the subsurface from the extreme temperature variations. This property means that while the surface experiences enormous temperature swings, areas just a few meters below remain at a more constant temperature. Planetary scientists have proposed that future missions might utilize this temperature gradient, positioning sensitive equipment below the surface while operating solar panels or radiators above. Mercury's extreme dayside heat would cause most conventional materials to fail through various mechanisms. Plastics would soften and deform at temperatures well below Mercury's daytime extremes. Rubber compounds would quickly degrade, losing elasticity and becoming brittle. Lubricants would evaporate rapidly in the heat and vacuum, causing mechanical systems to seize. These material limitations mean that Mercury exploration equipment would require exotic materials and designs not needed for missions to other planets. Passage 4. As punishing as Mercury's dayside temperatures are, the night side presents equally extreme conditions in the opposite direction. When the sun sets on Mercury, temperatures plummet rapidly without an atmosphere to retain heat. Nighttime temperatures fall to -170 degrees Celsius, or -274 degrees Fahrenheit. This extreme cold creates conditions nearly as challenging as the dayside heat, particularly for mechanical and electronic systems. The transition from day to night on Mercury creates extraordinary thermal stress. As the slow sunset progresses, surface temperatures drop hundreds of degrees over a period of Earth days. This cooling occurs fastest at the exact moment of sunset, with the temperature falling approximately 10 Celsius per Earth day. Any materials or structures on the surface would experience significant contraction during this cooling phase, creating stress that could lead to structural failure over repeated cycles. The frigid night-side temperatures approach the point where many gases condense into liquids or solids. Nitrogen would liquefy at these temperatures, while carbon dioxide would freeze solid. Even oxygen would approach its condensation point. These cryogenic conditions would affect the function of any equipment not specifically designed for extreme cold. Materials become brittle, fluids thicken or freeze, and electronic components operate unpredictably if at all. The extreme cold on Mercury's night side challenges power storage systems. Battery performance decreases dramatically at very low temperatures as chemical reactions slow down. Some battery types lose more than 50% of their capacity when operating below freezing, with performance dropping further as temperatures continue to fall. The cryogenic conditions on Mercury's night side would render most conventional batteries completely inoperable without significant heating systems. Mercury's lack of atmosphere means there is no wind chill effect, but the cold remains just as dangerous. Any exposed metal would become cold enough to instantly freeze human tissue on contact, similar to the effect of touching ultra-cold substances like liquid nitrogen. The extreme cold would penetrate insulation much more quickly than on Earth due to the vacuum environment, which eliminates insulating air pockets and allows heat to escape solely through radiation. The rapid temperature change at the day-night boundary, called the terminator, creates one of the most challenging environments on Mercury. As the terminator sweeps slowly across the surface during Mercury's rotation, it creates a moving zone of extreme temperature gradient. This transition zone experiences temperature changes of hundreds of degrees over relatively short distances. Equipment designed to function across this boundary would need extraordinary thermal management capabilities. Mercury's poles contain regions that never receive direct sunlight. These permanently shadowed craters, similar to those found on Earth's moon, maintain temperatures below -190 degrees Celsius, or -310 degrees Fahrenheit. These cold traps collect volatile materials that cannot exist in Mercury's hot regions. Radar observations from Earth and the Messenger spacecraft have indicated the presence of water ice in these permanently shadowed regions, preserved for potentially billions of years. The discovery of water ice at Mercury's poles surprised many scientists. Evidence suggests these deposits could be several meters thick in some areas. The ice likely originated from comet impacts over billions of years, with the water molecules migrating across the surface until reaching the cold traps at the poles. These ice deposits remain stable only because they never receive direct sunlight and exist in temperatures cold enough to prevent sublimation, which is the direct transition from solid to gas. The presence of ice on such a hot planet creates an interesting dichotomy. While equatorial regions experience temperatures hot enough to melt lead, the poles harbor frozen water and potentially other volatile compounds. This extreme environment gradient means that different regions of Mercury would require entirely different exploration approaches and technologies. A rover designed for the equatorial regions would likely fail completely if it attempted to explore the polar regions. The extreme cold of Mercury's night side causes materials to contract significantly. Different materials contract at different rates, creating stress at joints between components made of dissimilar substances. This thermal contraction can cause seals to leak, electronic connections to fail, and structural elements to crack. Engineers designing equipment for Mercury would need to account for the full range of thermal expansion and contraction, a challenge not faced to this extreme degree on other planetary missions. Lubricants present a particular challenge in Mercury's environment. Conventional oils and greases would evaporate quickly in the vacuum and heat of the day side, while freezing solid in the cold of the night side. Space mechanisms typically use special low-outgassing lubricants, but even these have operating temperature ranges narrower than Mercury's extremes. Dry lubricants like molybdenum disulfide or tungsten disulfide might function across a wider temperature range, but still face limitations in Mercury's harsh conditions. The night side cold would affect electronic systems in multiple ways. Semiconductor performance changes at very low temperatures, altering the function of computer systems and sensors. Solder joints and electrical connections experience stress from thermal contraction. Batteries and capacitors lose efficiency and capacity. These combined effects mean that any equipment expected to function during the Mercurian night would require either significant insulation and heating, or specialized electronics designed for cryogenic operation. During the long Mercurian night, no solar power would be available for approximately 88 Earth days. Any mission operating through the night cycle would need alternative power sources. Radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity, provide one potential solution. These power systems function independently of sunlight and actually operate more efficiently in cold environments where the temperature differential enhances their performance. The combination of extreme cold and hard vacuum creates conditions where some unusual physical processes can occur. Cold welding, where metal surfaces spontaneously fuse together upon contact, becomes more likely in these conditions. Materials can become super brittle, shattering from impacts they would normally absorb. Static electricity builds up more readily without an atmosphere to dissipate charges. These phenomena create additional engineering challenges for equipment operating during Mercury's night. Mercury rotates so slowly that certain locations near the poles experience prolonged periods in partial sunlight. These regions, called hot poles, maintain more moderate temperatures than either the fully illuminated or fully shadowed areas. Some scientists have suggested that these intermediate zones might prove less challenging for exploration, potentially offering a compromise between the extreme heat of direct sunlight and the extreme cold of permanent shadow. These regions might be priority targets for future landing missions. Passage 5. The third major hazard on Mercury comes from radiation exposure. Mercury receives an overwhelming amount of solar radiation due to its proximity to the Sun. Without an atmosphere to filter this radiation, the surface experiences the full intensity of solar output. This includes not just visible light and heat, but also ultraviolet radiation, X-rays, and high-energy particles. The radiation environment on Mercury would quickly prove fatal to any unprotected human and damaging to most electronic systems. Solar radiation at Mercury's distance measures approximately 6 to 7 times more intense than what we experience on Earth. This radiation includes the full electromagnetic spectrum, from radio waves to gamma rays. The most dangerous components for human health include ultraviolet radiation, X-rays, and gamma rays, all of which can damage DNA and cellular structures. Earth's atmosphere blocks most of these harmful wavelengths, but Mercury's surface receives them unfiltered. The Sun regularly produces solar flares, which are sudden releases of energy from the Sun's surface. These events send bursts of radiation and charged particles streaming through the solar system. Mercury, being closest to the Sun, receives the highest concentration of this radiation, with minimal warning time. A solar flare that might cause minor radio disruptions on Earth could deliver potentially lethal radiation doses to an explorer on Mercury. The unpredictability of these events adds another layer of danger to Mercury exploration. Even more dangerous than solar flares are coronal mass ejections, or CMEs. These massive eruptions from the Sun's corona eject billions of tons of charged particles into space. When these particles reach Mercury, they interact with its weak magnetic field and surface materials. The radiation dose from a significant CME could exceed lethal levels for humans, even behind substantial shielding. The particles can also cause electronic failures through single-event upsets, where particle impacts change the state of electronic components. Mercury's weak magnetic field provides minimal protection from solar radiation, Earth's much stronger magnetic field deflects much of the solar wind around our planet, creating a protective bubble called the magnetosphere. Mercury's magnetic field, at just 1% the strength of Earth's, cannot provide comparable protection. Additionally, the field appears offset from the planet's center, creating regions where the surface has even less magnetic shielding than others. This uneven protection complicates mission planning and risk assessment. The solar wind, a continuous stream of charged particles flowing from the sun, constantly bombards Mercury's surface. These particles, primarily electrons and protons, travel at speeds between 300 and 800 kilometers per second. When they strike Mercury's surface, they can cause sputtering, where atoms are knocked free from surface materials. Over billions of years, this process has contributed to Mercury's thin exosphere and the space weathering of surface materials. Galactic cosmic rays present another radiation hazard on Mercury. These extremely high-energy particles originate from outside our solar system, likely from supernovae and other energetic cosmic events. Earth's magnetic field and atmosphere provide significant protection from these particles, but Mercury's weak magnetic field allows most cosmic rays to reach the surface unimpeded. These particles can penetrate meters of shielding and cause radiation damage to both living tissue and electronic components. The radiation environment on Mercury would quickly damage unprotected camera systems and optical equipment. Radiation causes darkening in glass and transparent materials, reducing visibility through viewports or camera lenses. Image sensors experience increased noise and eventual failure when exposed to high radiation levels. These effects would compromise the visual systems necessary for navigation and scientific observation. Specialized radiation-hardened optics would be essential for any Mercury surface mission. Mercury experiences a phenomenon called surface charging due to its radiation environment. As solar radiation and charged particles strike the surface, they can build up static electrical charges in the regolith. Without an atmosphere to dissipate these charges, significant voltage potentials can develop between differently illuminated areas. This charging effect can damage electronic equipment and potentially create dust levitation, where charged particles of regolith are repelled from the surface and hover above it. This electrostatic environment creates additional challenges for surface operations. The radiation exposure on Mercury's surface would quickly exceed safe limits for humans. Space agencies typically limit astronaut radiation exposure to no more than 1,000 millisieverts over an entire career. On Mercury's surface, this limit could be reached within days or even hours during periods of high solar activity. Even with substantial shielding, the radiation environment would make human exploration extremely dangerous. Remote or robotic exploration remains the only viable approach for the foreseeable future. Solar ultraviolet radiation would cause rapid degradation of many materials on Mercury's surface. Plastics and polymers, commonly used in spacesuits and equipment, break down under ultraviolet exposure. This degradation weakens structural integrity and changes optical properties. On Earth, UV-resistant materials might last years in sunlight, but on Mercury, similar materials could degrade within hours or days due to the intensity of radiation. This material breakdown creates significant design challenges for Mercury exploration equipment. Mercury's position close to the Sun means it receives not just more radiation, but different proportions of radiation wavelengths compared to Earth. The Sun's corona emits extreme ultraviolet and X-ray radiation that is largely absorbed by Earth's upper atmosphere. Mercury has no such protection, resulting in surface exposure to these highly energetic wavelengths. These wavelengths cause ionization in materials they strike, damaging chemical bonds and altering material properties. Few common materials can withstand prolonged exposure to this type of radiation. The combination of radiation and temperature extremes creates synergistic degradation effects. Materials often break down more quickly when exposed to both radiation and heat simultaneously than they would from either hazard alone. This combined effect accelerates the deterioration of surfaces, coatings, electronics, and structural components. Engineering for the Mercury environment requires considering these compound stressors rather than addressing each hazard in isolation. The interaction between different environmental factors often proves more challenging than any single factor. Mercury's low gravity, about 38% of Earth's, interacts with the radiation environment in interesting ways. Secondary particles, created when radiation strikes the surface, can travel farther in Mercury's lower gravity. This extends the range of radiation effects beyond the initial impact site. Additionally, The lower escape velocity makes it easier for energetic particles created by impacts to escape into space, contributing to Mercury's tenuous exosphere. These gravity-related effects influence how radiation interacts with the planet's surface. The solar radiation at Mercury heats the surface unevenly depending on albedo, or reflectivity. Darker materials absorb more radiation and heat more quickly, while lighter materials reflect more energy back to space. This differential heating contributes to the mechanical breakdown of surface rocks through thermal stress. Combined with radiation damage, this process gradually pulverizes surface materials into regolith. The resulting fine dust would pose significant challenges for mechanical systems operating on the surface. Mercury's radiation environment causes a phenomenon known as space weathering. This process alters the appearance and composition of surface materials over time. Space weathering typically darkens and reddens materials, making them appear different than they would on Earth. This effect complicates remote sensing efforts, as the optical properties of materials change due to radiation exposure. Scientists must account for space weathering when interpreting data about Mercury's surface composition. The radiation on Mercury affects different materials in different ways. Metals tend to become more brittle under radiation exposure, potentially developing microfractures that can lead to structural failure. Ceramics may discolor and develop defects in their crystal structure. Semiconductors, the foundation of modern electronics, experience lattice displacement damage that alters their electrical properties. These material changes accumulate over time, gradually degrading performance until components fail. Radiation shielding presents a complex challenge on Mercury. Effective radiation shields typically use dense materials like lead, water, or polyethylene to absorb or deflect radiation. However, these shields add significant mass to spacecraft, increasing launch costs and reducing mobility. The extreme radiation environment on Mercury would require unusually thick shielding, making traditional approaches impractical. Engineers would need to develop innovative shielding solutions specifically for Mercury's conditions. The unique radiation effect on Mercury involves secondary radiation. When high-energy particles strike Mercury's surface, they can generate secondary radiation through nuclear interactions with surface materials. These secondary particles, including neutrons and gamma rays, create an additional radiation field above the surface. This secondary radiation can penetrate shielding differently than the primary radiation, potentially reaching sensitive equipment or biology that might otherwise be protected. Mission planners must account for both primary and secondary radiation sources. Radiation effects accumulate over time, a phenomenon called total ionizing dose. Electronic components have specific tolerance levels for radiation exposure, measured in rads or grays. Once these levels are exceeded, components begin to experience performance degradation and eventually failure. On Mercury, the total ionizing dose would accumulate much more rapidly than in other space environments, significantly shortening the operational lifespan of equipment. This accelerated aging effect necessitates either frequent replacement or extraordinary radiation hardening. Solar particle events, including flares and coronal mass ejections, occur with some regularity but remain difficult to predict precisely. The Sun operates on an approximately 11-year cycle of activity, with more frequent and intense events during solar maximum. A mission to Mercury would face significantly greater radiation risks during solar maximum periods. Mission planners would likely target solar minimum periods for Mercury exploration to reduce radiation exposure, though the baseline radiation levels would remain dangerous even during quiet solar periods. Solar radiation can cause an effect called photodistortion on Mercury's surface. In this process, sunlight causes atoms and molecules to be released from surface materials into the exosphere. This effect contributes to the composition of Mercury's tenuous atmosphere and the ongoing loss of volatile elements from the surface. Photodistortion works alongside sputtering from particle impacts to continually modify the surface composition. These processes have operated for billions of years, gradually changing Mercury's surface chemistry. The radiation on Mercury affects different regions of the surface to varying degrees. Areas near the equator receive the most intense radiation due to the more direct angle of sunlight. Polar regions receive sunlight at a much shallower angle, reducing the intensity per unit area. Permanently shadowed craters at the poles receive virtually no direct solar radiation, though they still experience cosmic rays and secondary radiation. This variation creates a gradient of radiation exposure across Mercury's surface. Even radiation-hardened electronics designed for space applications would face shortened lifespans on Mercury. Components certified for missions to Mars or Jupiter might last only a fraction of their expected lifetime in Mercury's more intense radiation environment. This accelerated degradation would require either frequent replacement of components, redundant systems, or development of ultra-radiation hardened electronics specifically for Mercury missions. Each approach carries significant cost and engineering challenges. Radiation effects on optical systems include darkening of glass and degradation of mirror coatings. These changes reduce light transmission and reflection efficiency, gradually diminishing the performance of cameras, spectrometers, and other optical instruments. Scientific instruments rely on precise optical properties for accurate measurements, making radiation-induced changes particularly problematic. Mercury missions would require specially designed optical systems with radiation-resistant materials or frequent recalibration to account for degradation. The cumulative radiation dose on Mercury creates unique challenges for mission duration. While Mars rovers have operated for years or even decades, equivalent hardware on Mercury might function for only weeks or months before radiation damage caused critical failures. This limited lifespan means that Mercury missions would need to accomplish their objectives quickly or incorporate extraordinary radiation protection measures. The cost-benefit analysis of Mercury exploration must account for these shortened mission timelines compared to other planetary destinations. Micrometeorite impacts represent another hazard on Mercury's surface. Without an atmosphere to burn up small particles, even tiny meteorites strike the surface at full cosmic velocities, typically tens of kilometers per second. These impacts create miniature explosions that erode equipment surfaces over time. The combination of micrometeorite impacts and radiation damage creates a particularly harsh environment for exposed surfaces, accelerating wear beyond what either factor would cause independently. Protective shields or sacrificial layers would be necessary for long-duration surface equipment. Mercury's extreme day-night temperature cycle interacts with radiation effects in complex ways. Materials expand and contract with temperature changes, potentially exposing new surfaces to radiation damage. Some radiation effects are temperature-dependent, accelerating at higher temperatures. The combined cycling of temperature and continued radiation exposure creates material stresses beyond what laboratory testing typically evaluates. This complex interaction of environmental factors makes predicting component lifetimes particularly challenging for Mercury missions. The radiation environment near Mercury affects not just the planet's surface but also the surrounding space. Spacecraft orbiting Mercury would experience the same intense radiation without the minimal protection of Mercury's magnetic field. Orbital missions must incorporate significant radiation shielding for sensitive electronics and provide protected environments for any potential future human crews. The Messenger mission to Mercury incorporated a sunshade and minimized the use of vulnerable solar panels to address these radiation challenges. Cumulative radiation exposure creates subtle effects that may not immediately cause failures but reduce reliability over time. Electronic components may begin operating outside their specified parameters, mechanical properties of materials may change, and thermal control systems may become less effective. These gradual changes increase the probability of mission-ending failures as exposure time increases. The radiation environment effectively places an upper limit on reliable mission duration, regardless of other factors like power or mechanical wear. Passage beyond radiation, temperature, and the lack of atmosphere, Mercury presents additional challenges through its surface terrain. The planet's surface features extensive cratering from billions of years of meteorite impacts. These craters range from small pits to massive impact basins hundreds of kilometers across. The largest recognized impact feature, the Caloris Basin, spans approximately 1,500 kilometers in diameter, comparable to the distance from London to Budapest. This heavily cratered landscape creates significant navigation challenges for any surface exploration. Mercury's surface bears the scars of its violent history. Without erosion from wind or water, impact craters remain clearly visible for billions of years. The oldest surfaces on Mercury may date back more than 4 billion years, preserving a record of the early solar system. This ancient landscape provides valuable scientific information, but creates treacherous terrain for exploration vehicles. Steep crater walls, boulder fields, and fine dust all present mobility challenges for rovers or landers. The surface gravity on Mercury measures about 3.5 meters per second squared, or roughly 38% of Earth's gravity. This reduced gravity affects how vehicles would interact with the surface. While lower gravity might seem advantageous for mobility, It also reduces traction, making it easier for wheels to slip on loose regolith or steep slopes. Rover design successful on Mars would need significant modifications to operate effectively in Mercury's lower gravity environment. Mercury's surface features strange formations called hollows, shallow irregular depressions that appear bright compared to surrounding terrain. These features, discovered by the MESSENGER mission, seem unique to Mercury. Scientists believe hollows form when volatile components in the subsurface sublimate directly into gas when exposed to Mercury's harsh conditions. This ongoing process suggests that parts of Mercury's surface remain geologically active today. The presence of hollows indicates that the surface continues to evolve, potentially creating unstable terrain in some regions. The regolith, or surface material, on Mercury likely consists of fine particles created by billions of years of meteorite impacts and thermal cycling. This material would behave differently than soil on Earth, with sharp, angular particles that could be highly abrasive to mechanical components. The regolith depth varies across the surface, potentially concealing hazards beneath a deceptively smooth appearance. The fine nature of this material could create dust problems for mechanical joints, optical systems, and thermal radiators. Mercury exhibits interesting geological features called scarps, enormous cliff-like structures that can extend for hundreds of kilometers and reach heights of several kilometers. These features likely formed as Mercury cooled and contracted over billions of years, wrinkling the surface like a drying apple. Many scarps appear relatively young in geological terms, suggesting Mercury continues to contract slightly even today. These massive cliffs would present insurmountable obstacles for surface exploration, necessitating careful route planning for any rover mission. The planet's slow rotation creates another set of challenges. Mercury rotates on its axis once every 59 Earth days, while orbiting the Sun every 88 Earth days. This creates the unusual situation where a solar day on Mercury, from noon to noon, lasts approximately 176 Earth days. This prolonged day-night cycle means that any surface mission would need to endure either extremely long periods of darkness or extremely long periods of intense sunlight, depending on the landing site and timing. Mercury experiences a strange resonance between its rotation and orbit. It completes exactly 3 rotations for every 2 orbits around the Sun, a relationship called a 3-to-2 spin-orbit resonance. This precise relationship means that some longitudes on Mercury experience significantly more extreme solar heating than others. The subsolar points at perihelion, the locations directly facing the Sun when Mercury is closest to it, receive the most intense heating. Mission planners would need to carefully consider these longitudinal variations when selecting landing sites. The surface of Mercury shows evidence of past volcanic activity. Smooth plains cover approximately 27% of the surface, likely formed by ancient lava flows. While Mercury appears geologically inactive compared to Earth, evidence suggests volcanic activity continued until perhaps 1 billion years ago. These volcanic plains provide relatively flat terrain that might prove easier for rover traversal than the heavily cratered regions. However, the composition of these plains may differ from other areas, potentially presenting different challenges for surface operations. Mercury's proximity to the Sun creates challenging lighting conditions for surface operations. The Sun appears approximately 3 times larger in Mercury's sky than it does from Earth. This larger apparent size creates more intense shadows with less diffuse light. The stark contrast between light and shadow would complicate navigation and imaging, as cameras would struggle to capture details in both brightly lit and shadowed areas simultaneously. This lighting challenge requires specialized imaging systems with high dynamic range capabilities. The fine particles of Mercury's regolith might become charged through interaction with solar radiation. This electrostatic charging could cause dust to cling to surfaces, potentially coating solar panels, radiators, optical instruments, and mechanical components. The combination of electrostatically charged dust and the absence of wind to clear surfaces creates a persistent contamination problem. Similar issues have affected lunar missions, but Mercury's more intense radiation environment might exacerbate these effects. Mercury's weak magnetic field interacts with the solar wind to create a unique electrical environment. Charged particles from the Sun induce electrical currents in Mercury's surface, particularly in more conductive regions. These induced currents generate secondary magnetic fields that interact with the planet's intrinsic field in complex ways. The resulting electromagnetic environment could affect sensitive electronic equipment, potentially causing interference or unexpected behavior. Mission designers would need to account for these electromagnetic interactions when developing communication and scientific instruments. The planet's slow rotation means that the terminator, the line between day and night, moves across the surface at approximately 3.6 kilometers per hour at the equator. This slow transition creates an interesting zone where temperatures gradually fall from daytime extremes to nighttime lows. Some scientists have proposed that mobile exploration platforms might surf the terminator, moving with this transition zone to avoid both the extreme heat of full day and the extreme cold of deep night. This approach would require precise navigation and timing to maintain position within the habitable temperature band. Mercury's surface likely contains valuable resources, particularly metals like iron and titanium, as well as potentially useful volatile elements in permanently shadowed polar regions. However, accessing these resources would require overcoming the planet's extreme environment. In the distant future, Mercury's proximity to the Sun might make it valuable for solar energy collection, but the technological challenges of operating in such harsh conditions make any resource utilization scenarios highly speculative at present. The scientific value of Mercury exploration currently outweighs any practical resource potential. The planet's composition differs from Earth in significant ways. Mercury has an unusually large core for its size, with the metal core comprising approximately 60 to 70% of the planet's mass compared to about 33% for Earth. This large metallic core generates Mercury's weak magnetic field and results in a higher overall density than would be expected for a planet of its size. The surface composition shows lower amounts of iron oxide than the Moon or Mars, but higher concentrations of sulfur and potassium. These compositional differences affect how surface materials respond to the extreme environment. Passage 8. Mercury's unusual orbit contributes to its harsh surface conditions. The planet follows a highly elliptical path around the Sun, with its closest approach at just 29 million miles and its furthest at 43 million miles. This varying distance causes a significant change in the amount of solar energy reaching the surface. At perihelion, its closest approach to the Sun, Mercury receives about 2.5 times more solar energy than at aphelion, its furthest point. This orbital variation adds another layer of complexity to the already extreme temperature cycles. The combination of Mercury's elliptical orbit and its 3-to-2 spin-orbit resonance creates a strange pattern of day and night cycles. Some locations on Mercury experience a hot pole effect, where the Sun appears to stop in the sky, move backward briefly, and then continue forward again. This unusual apparent motion occurs because Mercury's orbital speed exceeds its rotational speed when closest to the Sun. The resulting complex insolation patterns create locations on Mercury that experience twice the average solar intensity of other areas at the same latitude. Mercury experiences no seasons in the traditional sense. Unlike Earth, with its tilted axis creating summer and winter, Mercury's rotational axis is nearly perpendicular to its orbital plane, with a tilt of less than 2 degrees. This minimal tilt means that polar regions remain permanently cold while equatorial regions experience extreme heat with every rotation. The lack of seasonal variation means that the harsh conditions at any given latitude remain relatively constant over Mercury's entire year. This consistency of conditions might simplify mission planning, but offers no relief from environmental extremes. The solar day on Mercury, from sunrise to sunrise at a given location, lasts approximately 176 Earth days. This means that a single location on Mercury's equator experiences 88 Earth days of continuous sunshine followed by 88 Earth days of darkness. The extended daylight period allows surface temperatures to reach their extreme maximum, while the prolonged night permits cooling to the extreme minimum. Any long-duration surface mission would need to address both environmental extremes unless specifically timed for the brief transition periods. Mercury shows evidence of a phenomenon called space weathering, where the surface materials change in appearance due to exposure to the harsh space environment. Similar effects occur on the Moon, but Mercury's proximity to the Sun accelerates these processes. Space weathering typically darkens and reddens surface materials, altering their spectral properties. This effect complicates remote sensing efforts to determine surface composition, as weathered materials appear different than fresh samples of the same composition. Scientists must apply complex corrections to interpret Mercury's surface chemistry accurately. The discovery of water ice at Mercury's poles surprised many scientists when first confirmed. Radar observations from Earth had suggested the possibility of ice in permanently shadowed polar craters, but the MESSENGER mission provided definitive evidence. The ice deposits likely originated from comet impacts over billions of years. Water molecules can briefly hop across Mercury's surface until reaching the extremely cold polar regions, where they become trapped permanently. These ice deposits remain stable only because they never receive direct sunlight and exist at temperatures below -180 degrees Celsius. Mercury experiences a full suite of space hazards beyond the major challenges already discussed. Micrometeoroid impacts continuously bombard the surface at velocities of tens of kilometers per second. Without an atmosphere to burn up these particles, even tiny objects create small craters and eject surface material. Over time, this meteoroid gardening turns the uppermost surface into a layer of shattered rock fragments and fine dust. This process constantly refreshes the surface, exposing new material to space weathering. The continuous bombardment would pose an erosion risk to surface equipment, gradually damaging exposed components. Communication with Earth from Mercury's surface presents significant challenges. The extreme environment affects radio equipment performance, potentially reducing transmission power and reception sensitivity. More importantly, Mercury's proximity to the Sun creates radio interference when the planet passes behind or close to the Sun from Earth's perspective. During these periods, which occur regularly due to Mercury's orbital pattern, communication might become impossible for days at a time. Mission planners would need to account for these communication blackouts in any surface mission design. Mercury's surface likely experiences electrical charging due to the solar wind and photoelectric effect. When sunlight or charged particles strike the surface, they can eject electrons, leaving a positive charge. In shadowed areas, electrons from the solar wind can accumulate, creating a negative charge. This differential charging can generate significant voltage potentials between sunlit and shadowed regions. These electric fields might cause dust levitation, where small particles lift off the surface and move under electrical forces. This electrodynamic environment could create additional hazards for surface equipment, especially for sensitive electronics and mechanical components. The combination of solar heating and Mercury's iron-rich core creates a unique thermal gradient through the planet. Heat flows from the still cooling core outward while solar radiation heats the surface. These opposing heat flows create a complex thermal environment in the subsurface, with depths that might maintain relatively stable temperatures despite the extreme surface variations. Future missions might potentially utilize this thermal gradient, placing sensitive equipment below the surface to avoid the extreme temperature swings. However, accessing the subsurface would require drilling or excavation capabilities that add complexity to mission design. Mercury's unusual composition compared to other terrestrial planets provides clues about the formation of the inner solar system. The planet has a higher proportion of metal to silicate rock than would be expected for its position. Several theories attempt to explain this anomaly, including the possibility that a giant impact stripped away much of Mercury's original crust and mantle. Understanding Mercury's composition and structure helps scientists refine models of planetary formation and evolution. This scientific value drives interest in Mercury exploration despite the extreme challenges involved. The Caloris Basin, Mercury's largest confirmed impact feature, created shock waves that traveled through the planet and converged on the opposite side. This convergence created a region of disrupted terrain called the Weird Terrain, featuring jumbled hills and valleys unlike the surrounding areas. This unusual feature demonstrates the planet-scale effects that large impacts can have. The Caloris impact event likely occurred early in Mercury's history, perhaps 4 billion years ago, and released energy equivalent to millions of nuclear weapons. Such massive impacts shaped Mercury's early surface and contributed to its current appearance. Mercury's tectonic features differ significantly from Earth's. While Earth's surface shows evidence of plate tectonics driven by mantle convection, Mercury's surface is dominated by thrust faults created by global contraction. As the planet's interior cooled over billions of years, the entire planet shrank slightly, wrinkling the surface like a drying apple. The resulting scarps, or cliff-like features, can extend for hundreds of kilometers and reach heights of several kilometers. Some of these features appear relatively young, suggesting that Mercury continues to contract slightly even today. This ongoing geological activity adds another dimension to Mercury's complex surface environment. The discovery of hollows on Mercury's surface represents one of the most intriguing findings from the MESSENGER mission. These shallow, irregular depressions appear bright compared to surrounding terrain, and seem to form when volatile components sublimate directly into gas. The presence of these features suggests that parts of Mercury's surface remain geologically active, with material still being removed through interaction with the harsh surface environment. The hollows appear to be unique to Mercury, not observed on other airless bodies like the Moon. Their presence indicates that our understanding of Mercury's composition and ongoing processes remains incomplete. Mercury's extreme environment has prevented the formation of many types of minerals common on Earth. Hydrated minerals, which contain water in their crystal structure, cannot form or persist in the hot vacuum of Mercury's dayside. Similarly, minerals that require moderate temperatures or atmospheric gases remain absent from Mercury's surface. The mineral assemblage on Mercury likely consists primarily of high-temperature silicates, metals, and sulfides, creating a surface composition unlike Earth's familiar rock. This exotic mineralogy would affect how a rover or lander interacts with the surface materials. Passage 9. Scientific exploration of Mercury began with Earth-based observations, but detailed understanding required dedicated spacecraft. The first mission to Mercury, Mariner 10, launched in 1973 and performed 3 flybys of the planet between 1974 and 1975. This pioneering mission mapped about 45% of Mercury's surface and discovered its weak magnetic field. Mariner 10 faced significant challenges due to Mercury's proximity to the Sun, including thermal management problems that threatened to overheat the spacecraft. These early challenges demonstrated the difficulties of Mercury exploration. After Mariner 10, Mercury received no further visitors until the Messenger mission, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging. Launched in 2004, Messenger performed 3 flybys before entering orbit around Mercury in 2011. The spacecraft orbited Mercury for 4 years, mapping the entire surface and collecting data on the planet's composition, geology, and environment. Messenger's design incorporated several features specifically to address Mercury's harsh conditions, including a sun shield and minimized solar panel exposure. The European Space Agency and Japan Aerospace Exploration Agency collaborated on the Bepi-Colombo mission, launched in 2018 and scheduled to begin orbiting Mercury in 2025. This sophisticated mission consists of 2 separate orbiters designed to study different aspects of Mercury. The Mercury Planetary Orbiter will study the surface and composition, while the Mercury Magnetospheric Orbiter will focus on the magnetic field and its interaction with the solar wind. Bepi-Colombo incorporates advanced thermal protection systems to survive Mercury's extreme environment, including high-temperature solar panels and multiple heat shields. No mission has yet attempted to land on Mercury's surface. The extreme conditions make landing far more challenging than missions to the Moon or Mars. Any Mercury lander would need to address several critical challenges simultaneously, including thermal management during descent and on the surface, radiation protection for sensitive electronics, and the ability to operate in either intense heat or extreme cold depending on the landing site and time. These combined challenges have so far prevented the development of Mercury lander missions, though concept studies continue to explore the possibilities. The scientific value of Mercury exploration stems from several unique characteristics. As the innermost planet, Mercury provides insights into the formation of rocky planets close to their stars. Its unusually large metallic core and thin silicate mantle suggest an unusual formation history, possibly including a massive impact that stripped away much of its original outer layers. Understanding Mercury helps scientists refine models of solar system formation and evolution. Additionally, studying how Mercury's surface responds to the extreme environment provides insights into fundamental physical and chemical processes. Mercury's surface gravity measures approximately 3.7 meters per second squared, about 38% of Earth's. This relatively low gravity affects how equipment would interact with the surface. Lander designs must account for the reduced gravity during touchdown to prevent bouncing or tipping. Rovers would have different traction characteristics than on higher gravity bodies like Earth or Mars. The lower gravity also means that dust disturbed by rover movement might remain airborne longer and settle over wider areas, potentially contaminating sensitive instruments or mechanisms. The discovery of water ice at Mercury's poles offers one of the most intriguing targets for future exploration. These permanently shadowed craters maintain temperatures below -180 degrees Celsius, preserving ice that may have accumulated from comet impacts over billions of years. These ice deposits potentially contain not just water but other volatile compounds that could provide insights into the delivery of water and organic materials to the inner solar system. Accessing these deposits would require operating in extremely cold conditions with minimal solar power available, presenting a different set of challenges than exploring the sunlit regions. The primary power source for most planetary missions, solar panels, faces contradictory challenges on Mercury. The abundant sunlight provides plenty of energy, but the extreme heat reduces solar cell efficiency and accelerates degradation. Mercury receives approximately 6 to 7 times more solar energy than Earth. requiring specialized panel designs that can handle this intense input while operating at high temperatures. Power systems for Mercury's night side present the opposite problem, requiring energy storage or alternative power sources to function through the 88 Earth days of darkness. Communications with Earth from Mercury's surface would experience variable delays and occasional blackouts. The distance between Earth and Mercury ranges from approximately 50 million to 200 million kilometers depending on their relative positions in their orbits. This variable distance creates a communication delay ranging from approximately 5 to 14 minutes each way. Additionally, when Mercury passes behind or close to the Sun from Earth's perspective, solar interference can block radio communications entirely for days at a time. Mission planners would need to design operations to accommodate these communication constraints. The scientific instruments needed for Mercury surface exploration would require significant modifications from those used on other planetary missions. Spectrometers, cameras, and other optical instruments would need protection from both thermal extremes and intense radiation. Mechanical sample collection systems would need to function reliably, despite the cycling between extreme heat and cold. Drill systems for subsurface access would need to operate in unknown material properties and varying temperatures. These instrumental challenges add another layer of complexity to Mercury's surface mission design. The corrosive effects of Mercury's environment extend beyond radiation and temperature. The surface likely contains sulfur compounds that become active at high temperatures, potentially reacting with spacecraft materials. The constant bombardment by micrometeorites creates a steady rain of fresh, unweathered material that might have higher chemical reactivity than stable surface deposits. Even the charged particles from the solar wind can cause sputtering, where atoms are directly removed from surface materials. These combined effects create a chemically aggressive environment that further challenges long-term surface operations. Operations on Mercury would require a high degree of autonomy due to communication limitations. The minimum 5-minute one-way communication delay means that real-time control from Earth remains impossible. Any emergency situations would need to be handled by onboard systems before human operators could even become aware of the problem. This necessity for autonomy adds complexity to mission software and increases the importance of robust, redundant systems. Artificial intelligence capabilities would likely play a significant role in any future Mercury surface missions. The timing of Mercury surface operations would critically affect mission success. A mission landing shortly before local sunset could take advantage of cooling temperatures to deploy and initialize systems before the extreme cold of night sets in. Conversely, a mission targeting the dawn terminator could begin operations as temperatures rise from the extreme cold, but before reaching the daytime maximum. The slow movement of the terminator, at approximately 3.6 kilometers per hour at the equator, potentially allows a mobile platform to surf this boundary to maintain operations in a more moderate temperature range. Mission duration for Mercury surface operations would likely be measured in days or weeks rather than the years achieved by Mars rovers. The harsh conditions would accelerate wear on components, degrade materials, and damage electronics much more rapidly than on other planetary bodies. Even with the most advanced thermal management and radiation protection, the cumulative effects of Mercury's environment would eventually overcome engineering safeguards. This limited lifespan means that Mercury surface missions would need to prioritize high-value science objectives that can be accomplished relatively quickly. The cost of Mercury surface exploration exceeds that of comparable missions to other destinations. The specialized thermal protection systems, radiation-hardened electronics, autonomous operation capabilities, and redundant systems needed for Mercury's environment significantly increase development expenses. Launch costs also increase due to Mercury's location deep in the Sun's gravity well, requiring more fuel to reach the planet than destinations like Mars. These combined factors make Mercury surface exploration a particularly expensive proposition, requiring compelling scientific justification to secure funding. Future missions to Mercury will likely focus initially on polar regions where conditions prove somewhat less extreme. The permanently shadowed craters at Mercury's poles maintain temperatures hundreds of degrees cooler than equatorial regions, potentially allowing longer mission durations. Additionally, the confirmed presence of water ice and potentially other volatile compounds makes these regions scientifically valuable. Exploring the nature and composition of these polar deposits could provide insights into the delivery of water to the inner solar system and the evolution of Mercury over billions of years. Conceptual designs for Mercury landers often incorporate innovative thermal management approaches. Some proposals suggest legs that minimize heat conduction from the surface, essentially thermal insulators that keep the lander body from direct contact with the hot ground. Others propose reflective shields deployed after landing to protect from direct solar radiation. Advanced radiator systems could potentially direct heat away from vital systems, even in the challenging thermal environment. The most promising designs typically combine multiple approaches to address the layered thermal management challenge. Mercury's regolith, the layer of pulverized rock covering the surface, likely possesses different properties than similar material on the Moon. The intense heating cycles, constant radiation exposure, and higher levels of certain elements like sulfur would create soil with unique characteristics. Future landing missions would need to account for these uncertain properties when designing landing systems. The regolith might prove more compressible, more cohesive, or more abrasive than lunar soil, each possibility presenting different challenges for landing legs, wheels, or sampling systems. The scientific instruments for a Mercury surface mission would require significant modifications from those used on other planetary bodies. Spectrometers would need protection from thermal extremes while maintaining precise alignment. Cameras would need special optics that can handle the intense thermal cycling without losing focus. Sample analysis systems would need to operate across a wide temperature range or include temperature stabilization systems. These specialized instrument requirements add complexity and mass to an already challenging mission profile. Innovative miniaturization approaches might help address these challenges. Mercury's weak magnetic field creates interesting opportunities for scientific investigation. The interaction between the solar wind and Mercury's magnetic field generates complex electromagnetic phenomena that could be studied from the surface. Instruments to measure magnetic field strength and fluctuations would provide valuable data on how the field protects, or fails to protect, different regions of the surface. Understanding Mercury's magnetic field could provide insights into the planet's internal structure and the dynamics of its large metallic core. This magnetosphere investigation represents one of several high-priority science objectives for future missions. The challenging Mercury environment drives innovation in spacecraft materials and systems. High-temperature electronics using silicon carbide or gallium nitride semiconductors could potentially operate in Mercury's daytime heat. Ceramic components might replace conventional plastics for structural elements. Multi-layer insulation with vacuum gaps could provide thermal isolation between the hot exterior and sensitive internal components. These technological developments for Mercury missions could potentially find applications in other extreme environments, both in space and on Earth. The push to overcome Mercury's challenges drives broader aerospace innovation. Power systems for Mercury surface operations present unique challenges. Traditional solar panels would generate excessive power during daytime, but none during the long night. Batteries capable of storing enough energy for 88 Earth days of night operations would be prohibitively massive. Radioisotope power systems, which generate electricity from radioactive decay heat, offer one potential solution but add complexity and cost. Some mission concepts propose hybrid approaches, using solar power during day operations and entering dormant modes during night periods. The power challenge remains one of the most significant obstacles to long-duration Mercury surface missions. The communications infrastructure for Mercury operations requires careful design. High-gain antennas would need precise pointing capabilities to maintain Earth contact, while managing thermal distortion of components. Radio frequencies must be selected to minimize solar interference during conjunction periods when Mercury passes near the Sun as seen from Earth. Data transmission rates would vary widely depending on the distance between Mercury and Earth in their respective orbits. These communication challenges necessitate sophisticated onboard data management to prioritize critical information during limited transmission windows. Mercury's slow rotation creates an interesting possibility for mission design. A lander positioned near the day-night terminator could potentially operate in a more moderate temperature range than one in full daylight or darkness. As the terminator moves across the surface at approximately 3.6 km per hour at the equator, a mobile platform might surf this boundary to maintain operations in the temperature transition zone. This approach would require precise navigation and timing, but could potentially extend mission duration beyond what would be possible in fixed locations. Engineering studies continue to explore this intriguing operational concept. The navigation environment on Mercury presents several challenges. Without a global positioning system or magnetic field reliable enough for compass navigation, surface vehicles would rely primarily on visual navigation, star tracking, and inertial measurement systems. The stark contrasts between brightly lit and shadowed areas complicate visual navigation. Landmark recognition systems would need to account for the changing appearance of features as lighting angles shift during Mercury's slow day-night cycle. These navigation challenges add another layer of complexity to Mercury's surface operations. Sample return missions from Mercury would face all the challenges of landing, plus the additional hurdle of launching from Mercury's surface. While Mercury's gravity measures only 38% of Earth's, the extreme thermal environment complicates rocket operations. Propellants must be kept at appropriate temperatures despite the external conditions, requiring sophisticated thermal management. Launch windows would be constrained by both the thermal environment and the need to align with favorable transfer orbits back to Earth. Despite these challenges, returning samples from Mercury remains a long-term scientific goal due to the valuable information they would provide about inner solar system formation. One intriguing target for future exploration involves Mercury's mysterious hollows, the shallow, bright depressions that appear to form through sublimation of volatile components. Understanding the composition and formation process of these unique features could provide insights into Mercury's interior composition and ongoing surface evolution. Studying hollows would require instruments capable of analyzing very subtle chemical changes at the surface while operating in the challenging thermal environment. The unusual nature of these features makes them a high-priority target despite the technical difficulties involved in studying them up close. Human exploration of Mercury remains firmly in the realm of science fiction for the foreseeable future. The radiation environment alone would exceed safe limits for astronauts within hours or days, even with substantial shielding. The thermal extremes would require habitat modules with unprecedented thermal management capabilities. Life support systems would need to function flawlessly for extended periods without possibility of rescue or resupply. While robotic exploration of Mercury continues to advance, human presence on the innermost planet remains beyond our current technological capabilities. The inhospitable nature of Mercury will likely restrict it to robotic exploration for generations to come. The economic justification for Mercury exploration rests primarily on scientific returns rather than resource utilization. Unlike the Moon or asteroids, which might eventually provide resources for space development, Mercury's extreme environment makes any resource extraction scenarios highly speculative. The scientific value comes from understanding solar system formation, planetary evolution, and the behavior of materials in extreme conditions. Mercury exploration pushes the boundaries of our engineering capabilities and helps develop technologies that could find applications in other challenging environments. These scientific and technological benefits provide the primary justification for continued investment in Mercury missions. Advanced concepts for Mercury exploration include subsurface systems that might avoid the worst surface conditions. The temperature a few meters below Mercury's surface remains relatively constant and moderate compared to the extreme variations above. Boring or melting through the surface material to deploy sensors or even small mobile systems in this more stable environment could potentially allow much longer mission durations. These concepts remain technologically challenging but represent one potential approach to extending Mercury's surface science beyond the severe limitations imposed by surface conditions. Passage 11. Mercury holds vital clues about the formation and evolution of rocky planets. As the innermost planet, Mercury experienced a different formation environment than Earth, possibly affecting its unusual composition and structure. The high metal content of Mercury, with its core making up approximately 60 to 70% of its mass, suggests either unique formation conditions or a catastrophic impact that stripped away much of its original mantle. Understanding Mercury helps scientists refine models of how the inner solar system formed and evolved over its 4.5 billion year history. The surface of Mercury preserves a record of the early solar system, without erosion from wind or water, and with minimal volcanic resurfacing compared to Earth or Venus. Mercury's oldest terrains may date back more than 4 billion years. This preserved ancient surface provides insights into the period of heavy bombardment early in solar system history when impact rates were much higher than today. Studying Mercury's craters helps scientists understand this critical period in planetary evolution when the final stages of planet formation were still underway. Mercury's extreme environment creates a natural laboratory for testing the limits of materials and processes. The combination of vacuum, radiation, and temperature extremes exceeds conditions typically replicable in Earth laboratories. Observing how different surface materials weather under these conditions provides insights into fundamental physical and chemical processes. These observations help scientists understand phenomena like space weathering, which affects all airless bodies in the solar system but proceeds most rapidly on Mercury due to its harsh conditions. The presence of water ice at Mercury's poles raises intriguing questions about the delivery of volatiles to the inner solar system. Water and other volatile compounds likely arrived on Mercury via comet and asteroid impacts over billions of years. Understanding the composition, distribution, and age of these polar deposits helps scientists reconstruct the history of water in the inner solar system. This information bears directly on questions about Earth's own water supply and the potential habitability of rocky planets in general. The persistence of these ice deposits demonstrates how even the most hostile planetary environments can preserve important materials under the right conditions. Mercury's magnetic field provides a unique window into planetary magnetism. Most small rocky bodies, including Mars and Venus, lack significant global magnetic fields today. Mercury's field, while just 1% the strength of Earth's, suggests an active dynamo process in its large, partially molten metallic core. The field's unusual offset from the planet's center creates distinctive patterns in how it interacts with the solar wind. Studying Mercury's magnetosphere helps scientists understand the general principles of planetary magnetic fields and their protective effects. The extreme day-night temperature cycle on Mercury drives unique processes not seen on other planets. This thermal cycling causes rocks to expand and contract repeatedly, accelerating their breakdown into smaller fragments. The heating can drive volatile elements out of surface materials through thermal desorption, gradually changing surface composition. The cold of night might temporarily trap gases that are mobile during the day. These thermally driven processes create a dynamic surface environment despite the absence of air or water. Understanding these processes helps explain Mercury's current surface characteristics. Mercury experiences the most intense solar wind of any planet in our solar system. This stream of charged particles from the Sun interacts with Mercury's magnetic field and surface in complex ways. The solar wind can directly impact the surface in regions where the magnetic field provides insufficient protection, causing sputtering of atoms that contribute to Mercury's tenuous exosphere. These interactions create a dynamic system where material is continuously removed from the surface and temporarily suspended above it before either returning to the surface or being lost to space. This process gradually erodes Mercury's surface over billions of years. The challenging nature of Mercury exploration drives technological innovation. The extreme thermal environment requires advanced materials and cooling systems beyond those needed for other planetary missions. The intense radiation demands more robust radiation, hardening for electronics. The communication difficulties necessitate greater spacecraft autonomy. These technological challenges push the boundaries of what's possible in space engineering, potentially leading to breakthroughs applicable to other missions. The history of space exploration shows that tackling difficult destinations often yields unexpected technological benefits with wider applications. Mercury's proximity to the Sun creates navigational challenges for spacecraft. The Sun's gravity significantly affects trajectories, requiring precise calculations and frequent course corrections. The intense solar radiation puts pressure on spacecraft through the photon pressure effect, subtly altering orbits over time. These navigational complexities demand sophisticated flight dynamics calculations for mission planning. The Messenger mission demonstrated the feasibility of Mercury orbital operations despite these challenges, paving the way for more ambitious future missions like Bepi-Colombo and potential landers. The strange orbital resonance of Mercury, with exactly 3 rotations for every 2 orbits around the Sun, intrigues scientists studying celestial mechanics. This precise 3-to-2 spin-orbit resonance likely resulted from tidal interactions with the Sun over billions of years. The resonance creates a unique pattern of day and night that affects how surface features experience heating and cooling. Understanding how Mercury achieved and maintains this resonance provides insights into the long-term evolution of planetary rotation states, with potential applications to exoplanet studies where similar resonances might exist. Mercury's composition differs significantly from theoretical models based simply on its position in the solar nebula. The planet contains higher proportions of elements like potassium, thorium, and uranium than would be expected for a planet that formed so close to the Sun. This composition provides clues about the mixing of materials in the early solar system and the processes that distributed elements as the planets formed. Mercury's unexpectedly volatile rich composition suggests that our understanding of inner solar system formation remains incomplete. Future missions to Mercury will help refine these formation models. The hollow features on Mercury, discovered by the Messenger mission, represent one of the most intriguing geological processes in the solar system. These shallow depressions with bright interiors and halos appear to form when volatile components sublimate from the subsurface. The presence of these actively forming features suggests that Mercury's surface continues to evolve today. Understanding the composition and formation mechanism of hollows provides insights into Mercury's internal composition and the ongoing processes shaping its surface. These features may have no exact analog elsewhere in the solar system, highlighting Mercury's unique character. Mercury experiences space weather more intensely than any other planet. Solar flares, coronal mass ejections, and other solar disturbances impact Mercury with minimal warning time and maximum intensity. These events can temporarily alter the planet's magnetic field configuration, enhance surface charging, and increase the rate of material lost to space. Studying how Mercury responds to these solar events helps scientists understand space weather effects throughout the solar system. This knowledge proves increasingly important as human society becomes more dependent on space-based infrastructure vulnerable to space weather events. Mercury has no moons of its own, unlike most other planets in our solar system. This absence likely results from Mercury's proximity to the Sun, whose powerful gravity would disrupt the orbit of any potential satellite. The lack of a moon means Mercury experiences no significant tidal forces beyond those exerted by the Sun itself. This simplifies some aspects of Mercury's evolution while making it less useful for studying certain processes like tidal heating that play important roles for other planets. Mercury's moonless state represents another way its evolution differs from planets like Earth, Mars, or the gas giants. Mercury's core appears partially liquid based on analyses of its rotation and magnetic field. This liquid portion allows the generation of Mercury's magnetic field through dynamo processes similar to those operating in Earth's core, though at a much reduced intensity. The persistence of a partially molten core after 4.5 billion years provides information about Mercury's thermal evolution and internal composition. Heat sources like radioactive decay of elements such as uranium, thorium, and potassium likely contribute to maintaining this partially molten state. Understanding Mercury's internal structure helps scientists model the evolution of all terrestrial planets. Mercury appears at first glance similar to Earth's moon, sharing a heavily cratered appearance and airless environment. Closer examination reveals significant differences in density, composition, magnetic properties, and surface features. Mercury contains a much larger proportion of metal, exhibits unique tectonic features like scarps, possesses a global magnetic field, and shows evidence of more recent volcanic activity than the Moon. These differences highlight how similar appearing bodies can have radically different histories and properties. The comparison between Mercury and the Moon helps scientists understand the factors that drive divergent planetary evolution.